Hello. In the previous lectures, we have covered a great deal of introductory portion of postulatory approach to quantum mechanics. And I also stated the first, uh, what you can say, first postulate also. Today, I'm going to put a more stress individually on postulate number one. Okay. So in this series of lecture, what is my aim? My aim is to come up probably with individually, I'm going to touch upon all these postulates because they form the heart of your quantum mechanics. Okay, so this is how you're going to do the quantum mechanics. So let us first set these postulates and let us first understand these postulates in a manner that helps us in understanding quantum mechanics better. And this will also this will also enable you uh, in a way that you can understand different potential problems also. So basically, if you start with this postulates at first, and then you progress to the potential problems, you will be at a better place. Okay. Although, as I promised, there would be a separate lecture series on linear vector spaces. So you just keep in touch. Okay. So let us start. So, as we had done yesterday, I'm going to write the postulate number one. This particular lecture is completely on postulate number one only. So I'm just going to re-revise what I have done yesterday. So yesterday I wrote that yesterday I gave some definition kind of thing with of linear vector space and also of the Hilbert space. Today again I'm going to start with the same. So basically, the first postulate is regards the state of the system. It is regarding the state of the system. What does it mean? It means it says that the state of the system, state of a quantum system, is specified at each time t by a state vector. Okay, what is this? I'll come up. I have touched upon this, but I'll briefly touch upon this today also. So by a state vector in a Hilbert space. In a Hilbert space. Okay, and what is good about this particular site? It contains all the requisite information. It contains all the about the system which it represents. Okay. This is one thing. So again, yesterday I discussed what is a Hilbert space. Hilbert space is in itself a linear vector space. Or you can say it is a normed linear vector space. And what is norm? We'll touch again on this today. With inner product defined. With something called as inner product, which we yesterday related with the scalar product of two vectors. Okay. So my idea is that just understand all these things, just have an idea of all these things, because once we are going to start with linear vector space individually, we're going to get much of what I'm trying to write right now. Okay. So right now, even if you're not getting it to the complete entirety, don't worry about it. Okay. So first thing one needs to understand is that this particular Hilbert space is in itself a linear vector space. Okay. And yesterday, as I mentioned, linear vector space has certain properties. So for example, if I say that a set V forms a linear vector space over a field F. Okay, so if I say that set V forms a linear vector space over a field F. So what is a field? So field is another algebraic structure. So which which satisfies certain properties. So basically, V is also for example, here we knew here I told you that if I'm saying linear vector space, it requires me to have two things. That is, one is vectors, another is scalars, and there are certain operations defined over it. Okay, there are certain operations with regards to addition. These vectors form an abelian group, and with regards to scalar multiplication, there should be some properties like alpha into beta times v vector should be equals to alpha times beta v vector. Or you can say one of the property was existence of identity. Okay, another property was if I want to write alpha u vector plus v vector, then it is equals to alpha u vector plus alpha v vector. And let's say if this particular alpha v vector is belongs to some particular space. Let's say this belongs to uh, some particular space, and alpha, let's say beta, w vector also belongs to that space. Then their addition is also vector of the same space. Okay, so such properties, if these are the properties, you can just see them in yesterday's lecture also. And in addition, with another property was distributivity. If all these properties are satisfied, we say that the we say that the set V forms a linear vector space over F. Okay, so this is the first thing that you need to understand, that Hilbert space itself is a vector space. And in order to further define Hilbert space, one needs to understand that there should be a well-defined inner product. Or right now you can associate with something called as well-defined inner product. You can associate it with the scalar product. And there were certain properties. That is, if I'm doing an inner product of psi with respect to phi, then it is equals to conjugate of inner product phi plus comma psi. And similarly, if I okay, so another thing is, this particular scalar product happens to be linear. What do I mean when I say linear? So for example, it means that if I'm taking a scalar product of phi with respect to alpha psi 1 plus beta psi 2, it is equals to alpha phi comma psi 1 plus beta phi comma psi 2. So this is how it is, and it is anti-linear. It is anti-linear if this particular factors comes first. So for example, if I write alpha psi 1 plus beta psi 2, if it comes first and then there's a phi, then it happens to be psi star, alpha star. Have I made a mistake somewhere? Okay, psi 1 comma phi plus beta star psi 2 comma phi. Okay, so this is how we write. So it is anti-linear if this particular term comes in. Okay, so one has to understand that for defining Hilbert space, one thing is sure, that H must form a linear vector space. H must have elements of H. There must be a well-defined inner product. You can say inner product operation when it comes to the elements of these Hilbert space. And another property was some topological property, which is said that H must be separable. Okay, and another important property was H must be complete. Okay, what do I mean when I say complete? It means that if I take any Cauchy sequence psi n in psi n belongs to this Hilbert space H, then it should converge to some element of H only. This particular Cauchy sequence, which belongs to this Hilbert space H, must converge to some element in the Hilbert space itself. Okay. Okay. I hope in these are very you can say sort of you should just make a firm understanding. And I told you yesterday also that mostly we will be concerned with square integrable sorry, mostly we'll be interested with the square integrable or square summable function. So I'll come on these things today, and I'm going to elaborate a little bit on again on the linear vector space. Okay, so yesterday I tried to draw an analogy of linear vector space. Okay, linear vector space, and I actually left the lecture by saying that this kind of notation of representing psi is called as a Dirac notation, and this is what serves as a motivation of today's lecture. So what is a Dirac notation, and how it simplifies our working of quantum mechanics? Today we are going to see. But before we move on to linear vector space, let us understand what we mean when I say what do I mean when I say the dimensions of linear vector space? What do I mean when I say the dimensions of linear vector space? So let us consider that there is a set of n vectors. Let us consider a set of n, you can say non-zero vectors. N non-zero vectors. Let us say I'm writing it as phi1, phi2, phi3 dash 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 phi. Okay, they are said to be linearly independent. They are said to be linearly independent if summation an, sorry, ai phi I varying from 1 to n equal to 0 implies that all of these phi i's must be equal, all of these ai's must be equal to 0. If there is no other way out. So for example, if I'm saying that these phi1, phi2, phi3, phi8 are linearly independent to each other, then what does it mean? What do I want to say? What do I want to say? That if I write a linear combination of all these things and equate them up to 0, then the only solution left to us is that these coefficients individually must be equal to 0. All of them must be equal to 0. If this is the case, then these phi1, phi2, phi3 dash 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 phi n are said to be linearly independent. Okay. Okay. And if this is not the case, and if this is not the case, and the solution is such that not all of these coefficients are trivially 0. Okay, then we say that our system of all these n vectors, that is phi1, phi2, phi3 dash 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 phi, are linearly dependent. Okay, because if it so happens, what will happen? Let's say if there are some if this is equal to 0 and all of the AIs are not equal to 0, then what will happen? You can shift some of them here, and you can write this one of the vector as linear combination of other vectors. Okay, so if this happens to be the case, so let's say if all AIs are not equal to 0, then one of the vector indeed can be represented. One of the vector can indeed be represented as linear combination of other vectors. Linear combination of other vectors. And when we do so, we say that we are dealing with linearly dependent vectors. Okay. So now we are going to address the main question. The main question, that is the dimension. So what do I mean when I say dimension of linear vector space? When I say what is the dimension of linear vector space? Okay, this is what I'm going to teach. Okay, so what is the dimension of linear vector space? So it is nothing but it is the maximum number of, it is the maximum number of linearly independent vectors uh, the space can. So for example, if I'm dealing with a two-dimensional space, okay, if I'm dealing with a two-dimensional space, that is I cap and j cap, and if I just write that a I cap plus b j cap is equal to 0 I cap, that is 0, which implies 0 comma 0, it implies that a must be equal to 0 and b must be equal to 0. So these I cap and j cap are nothing but they are linearly independent to each other. I cap and j cap are linearly independent to each other. This is quite easy to see, quite easy to see geometrically also, because there is no projection of I cap over j and there is no projection of j cap over I. So these I cap and j cap form the what we call as the orthonormal set of vectors, because I dot I, if you take this, is going to be 1, and if I take I dot j, it is going to be 0. So basically I cap and j cap forms the orthonormal set of vectors for two-dimensional space. Okay, and for defining any of the vectors in this space, in this vector space, that is r square over r, or simply in Cartesian plane, any vector can be represented as a linear combination of I cap and j cap. So basically the dimension of this particular space will be 2. The dimension of this particular space would be 2. Okay. So in general, uh, if the maximum number of linearly independent, you can say, vectors in a space is Rn. So if maximum number of linear independent vectors in a space Rn, in a space Rn, then space would be called as a n-dimensional space. Then this particular space is called as the n-dimensional space. And any vector in this space can be written as linear combination, Okay, linear combination of these n linearly independent vectors. So let's say these vectors I'm defining by phi1, phi2, phi3, dash dash dash, phi n, capital N. Okay. Then any other vector in this particular space can be written as summation I equal to 1 to n, capital N, and some ai is there, and there is okay. Now we say that this particular space is spanned by these two vectors. Okay. Basically, when we say this particular space is spanned by two vectors, I mean any vector in this particular two-dimensional space can be represented as linear combination of I cap and j cap. And similarly, in n-dimensional space, I would say that this n-dimensional space is spanned by all these n linearly independent vectors. And all these vectors are said to form the basis, So let us first write what is basis. These are just definitions, okay? So don't worry about all these things. Just understand, okay? Just understand. What is basis? So basis is like, for example, for this n-dimensional space, these are the bases, okay? So I would write the basis of a vector space of a vector space uh, uh, contains, or you can say it consists of a set of maximum possible linearly in linearly independent vectors belonging to that space. Okay, so we are going to see all these things when in particular for R square. Okay, so that you can understand. Okay, in particular, we choose that all these vectors, that is which form the basis, that is phi 1, phi 2, phi 3 dash 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 phi n, are orthonormal to each other. What do I mean when I say orthonormal to each other? It implies that that is scalar product phi I comma phi j is equals to Dirac ij. That is, if I is equal to j, then it is equal to 1, otherwise it is 0. Okay, and if I can write if I can say that my basis, if the basis spans the complete space, okay, if the basis spans the complete space, or you can say the entire space, if basis spans the entire space, then this particular space is said to be complete. We say that space is complete when the basis spans the entire space. So for example, if I cap and j cap are such two orthonormal vectors which span the entire R square, so these bases are said to span the space, and that particular space is called is actually complete. Okay, that is, we do not require any other basis vector for completing the space. So basically, for R square, I cap and j cap would serve our purpose in order to span the entire space. Okay, so I hope this is quite clear to you. Now let us move to the idea of, let us understand this idea of vector space. So basically, why we are doing it? Because we want to understand what is a Hilbert space. So Hilbert space is again a vector space with two of the properties. One of the properties that one I have already discussed, that is it must be complete. Okay, so you just understand by completeness. I have yesterday also explained. And another thing that we need to understand is that why we are using this Dirac notation, because of which I'm doing this lecture. And this inner product must be defined. If inner product is defined, then this all these properties, when contained, that is H is a linear vector space, there must be a well-defined inner product in H. H must be separable and then H must be complete. Then these all properties qualify the statement for defining that H is a Hilbert space. Okay, so and basically all these wave functions are picked from the Hilbert space, and squarely integrable function are one such category of, you can say, sort of Hilbert space, such you can say squarely integral functions that we are going to deal in quantum mechanics. And why we are dealing squarely integral functions? Because we know that the probability of finding a particle anywhere in the space is governed by a squarely integrable quantity. So one needs to understand that this set of squarely integrable functions actually form a linear vector space, and also forms a Hilbert space, so to speak. Therefore, these are very important. So these class of functions are very important for us. So now just try to formulate whatever I told about in context to R square, because yesterday also I explained it using R square because it is something that you know from your childhood. Okay, so I'm discussing R square over R. So one can understand that what are the basis vectors for the R square. So I told you I cap and J cap. Okay, I cap and J cap. Often it is very important, it is quite convenient to write all these vectors in form of matrices. So basically, there are two standard basis vectors. as you know, that is I cap and j cap. You will write instead of I cap j cap ey and ex and ey. And what is ey? So if you make the directional cosine of ex, it will be 1 comma 0. So instead of writing 1 comma 0, I'll write in column, and this ey would be 0 comma 1. Okay, I cap plus 0 j cap, 0 I cap plus 1 j cap. So basically I have written it in column form. And it's quite easy to see that if I'm doing ex dot ex, I told you yesterday, when if I'm doing this scalar product, so basically I have to take a transpose of it, complex transpose of it, but right now conjugate transpose, but right now this is so this is equal to 1. So this is these are real entries. If I write ex dot ey, so this will be again, I think 1 comma 0, and here you will get sorry, okay, and this is 0 comma 1, and you'll get a 0. So clearly these two ex and ey form orthonormal set of vectors. These forms orthonormal set of vectors. And we know that any vector in R square can be represented as the linear combination of I cap and j cap. So basically, instead of I cap j cap, I'm writing ex cap plus ey cap. Okay. Now, clearly, yesterday also I told you that this R square over R forms a vector space. So this forms a linear vector space. So R square forms a linear vector space over R. And similarly, we can extend the idea to R cube over R, and we can extend the idea to Rn over R. Okay. In fact, real number system also form a vector space. Basically, all these are going to be a vector space over R. Okay. So if I tell about Rn, R cube, sorry, what will be the standard basis vectors? The standard basis vectors for R cap would be R cube will be I cap, that is ex cap, that is 1 0 0. Ey cap would be 0 1 0. And what would be Ez cap? Ez cap would be 0 0 1. And similarly, if I want to write what would be the standard basis vectors for Rn? So this will be nothing, but this would be 1 0 0 0 dash dash dash. This would be n. Then this is 1 0 1 0 0 0 0 dash again, and so on and so forth. Okay, so these set of n linearly independent vectors, these are the set of n linearly independent vectors which are going to span the entire Rn, or you can say these are all the basis vectors. These are all the standard basis vectors. So why these are standard basis vectors? So if I just take any let's say any element in Rn, let's say x1, x2, x3 dash 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 xn, it is nothing but it is equal to what? It is equal to, let's say, if I'm writing it as e1 cap, this is e2 cap, and dash dash dash. Let's say this is en cap. So I can write it as x1 e1 cap plus x2 e2 cap dash 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 xn en cap. So I can write any vector in this Rn space as linear combination of e1, e2, e3 dash 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 en. So basically these e1, e2, en span e1, e2, e3 dash 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 en span the entire n-dimensional space. Okay. Okay. Now you see this, what if it all it happens that if at all it happens that summation I equal to 1 to infinity xi mod ka whole square is finite, then we say that our xi's, that is x1, x2, x3, xn, are square summable, are square summable. They are square summable. And this is something that we can extend for our functions as well. This is what we can extend to our functions as well. So a space of square integrable functions also forms a Hilbert space, which is denoted by L square, is one where this kind of integration, that is from minus infinite to plus infinite, psi x mod ka whole square dx is defined and it is finite. Okay, so the element size in this space of square integrable functions are such that minus infinite to infinite psi mod ka whole square dx is less than infinity. That is, this particular integration is a finite integration. Okay, now you see, one thing is very much clear. That in order to understand about vector spaces, you can have matrices. You can take the examples of functions. So yesterday I told you one of the example was the set of all continuous functions. Set of all continuous functions also form a linear vector space. So here these functions are vectors. So set of all real continuous functions forms a linear vector space. Okay, so why? Because you see, if you take continuous functions, so sum of two continuous function is again a continuous function. By algebra of continuous function, we know that sum of two, or sum of, let's say, n continuous functions again form a continuous function. Okay, now if I check the property of, let's say, if I'm just doing it on two functions, so f1 plus f2 is equal to f2 plus f1, commutativity holds, associativity holds, closure has we can see that I have written closure at the very first instance itself. And then you know that the constant function is also a continuous function, and in particular zero function is also a continuous function. So 0 plus f is equal to f plus 0 is equal to again f. If f is a continuous function, then minus f is also a continuous function, so on and so forth. And similarly, you can also check the properties of scalar multiplication. One can understand that set of all these real continuous functions form a linear vector space. So not only these r square, rn, these are linear vector spaces. Even these functions can form vector spaces. So you just don't have some certain sense of don't keep certain sense of preoccupation. We can have in form of vectors, we can have functions as well. Okay, we can have functions as well. But one thing is very much sure, that if I'm saying that if a vector v belongs to f, let's say space v, and w vector also belongs to v, then all these properties, when I'm applying, that is these vector additions, if I'm applying, then the resultant must also belong to v. That is what I want to say, that if I'm saying that in order to qualify the statement for vector spaces, if I'm taking v vector as a vector which is from vector space v, another w vector from vector space v, if I'm adding them up, then again it should be continuing v. Okay, now let's say I'm talking in particular for column vectors. So if I'm saying a column vector, if column vector is there and if I'm adding to a row vector, can this be possible? No, it cannot be possible. It cannot be possible. So what needs to be done? So one needs to understand that if I'm taking column vectors, I can only take column vectors in a space. I cannot take rows in that particular space, because I know that I cannot perform a vector addition. I cannot perform this kind of addition. Okay, this addition is not well defined. Okay, this is not defined. So one has to understand that if I'm let's say if I'm defining a vector space using column vectors, then I cannot have a row vector. And if I'm doing with respect to row vector, I cannot have a column vector. Okay. Now this brings us to something called as the dual of a vector space. What I'm writing dual of a vector space. So what happens is that if I want to formulate some theory with regards to the rows, then I need to define something called as a dual of a vector space. So I'm now right now defining something called as the dual of the vector space. Just let me write it in brief what I want to convey. Okay, just give me a minute. Okay. And incidentally, there's a theorem in linear algebra which suggests that every linear vector space, every linear vector space has a dual space. And in fact, this particular dual space also forms a vector space. I should write which also forms a vector space. So corresponding to column vector, the dual space will be formed by the row vector. Individually, these row vectors, if you just take them into consideration and apply all the properties of vector space, you'll be able to find that this also satisfies the condition for the conditions for the vector space. So every linear vector space has a dual space which also forms a linear vector space. So for example, if 1 and 0 and let's say 0 and 1 are some you can say states in a linear vector space, then obviously in that particular vector space you cannot have 0 1 and 1 0, okay, in rows, but a dual space corresponding to this would contain them. So dual space would contain 0 1 0 and 0 1. So this will be contained in the dual space. Okay, now this is I mean I have not written very rigorous kind of derivation, rigorous kind of definition, just for making you understand that for every vector space there is a dual space which also forms a vector space. So basically these are the elements of the dual space to this these so if these column vectors are contained in a vector space, this is the dual space. So these are the vectors in the dual space. Okay, now what is a Dirac notation? So in quantum mechanics, you'll find that we are going to represent these column vectors by something called as kets. And correspondingly to the kets, there are corresponding to the ket vectors in the dual space, there are something called as bra vectors. Okay, so these notations are very important, and they're going to make our quantum mechanics quite easy and quite you can say that there is a lot sense of clarity when it comes to working with these bra and ket notations. Okay, so let us just write a few of the things. So I wrote initially that the state of the system, the physical state of system, is characterized by a wave function, and I represented it in ket notation. Okay, so what are kets? So kets are nothing but these are the elements of vector space. These are elements of a vector space, and in particular, in quantum mechanics, sooner we are going to see that mostly the column vectors are represented as kets. Okay, so okay, and correspondingly to these kets in the dual space, basically dual space to this these are elements of a particular vector space, and corresponding to this vector space there would be dual space, and corresponding to these kets there would be bra vector in the dual space. So basically, if I'm going to denote it using this in the on the bra vector, I'm going to denote by this kind of notation, and this is certainly very convenient notation to use. So, for example, if I want to write a scalar product, if I want to write the scalar product, or you can say inner product with respect to, let's say, phi comma psi, if I want to write the scalar product in form of ket and bra notation, then this would be simply this. This would be simple. This. More particularly, if I'm writing it in the you can say uh, in what you can say uh, in form of integrals, then this would be like psi star phi, and this would be simply beta. Okay, we can also represent this is in coordinate space. We can represent it in momentum space also. All these things we are going to see later on, but just understand this is how you can represent your scalar product or inner product here. Okay, using these Kettler notations. So for for each of these, because let's say if these are kets are element of a particular vector space, and by vector space, because we know that if I'm talking about wave functions are supposedly the members of the Hilbert space, which themselves form a vector space. So let's say if I'm saying that there is a wave function psi, if I'm representing it as ket, then corresponding to this ket, there always would be a unique bra vector. First thing. Secondly, there always exists a one-to-one correspondence between the ket and bra. So basically, if I'm writing a psi plus b phi, corresponding to this ket vector, there would be a bra vector. All you need to take is a conjugate transpose. Okay, this is how. Then, as I told you, if these are the elements, psi is an element in the Hilbert space. So one needs to see, one needs to understand that inner product must be well defined. And I defined the inner product using these notations like this. So if I'm defining the inner product of phi with respect to psi, so this is phi. Like this is how I'm going to write, and then I can equate it to this by this. Okay, so you should understand that in quantum mechanics in general, all of these are complex numbers. So these orderings matter. So just don't. We should be very careful in applying all these results. Okay, so this is one thing. If I want to write it in integral formalism, then I'll write this. So phi star. This is phi star. So understand this is phi now. Okay, so this is phi means what? This is bra. So this is conjugate transpose. So phi star psi eta. Again, so let me just write it. It will be equals to what? It will be equals to integration psi star phi theta and whole transpose. Another thing is, I told you initially that Hilbert space are nothing but they are normed linear spaces. Non-linear spaces with inner product, with a defined inner product, with a well-defined inner product. So what do I mean when I say norm? So basically, if I'm saying norm, so let's say if I have this vector psi, if I'm defining norm, so norm would be this, which is nothing but it is psi mod ka. This particular thing must be real as well as positive. So norm must be real as well as positive. Must be real as well as positive. And this would be 0 only if this psi is 0. Otherwise, it will be non-zero and greater than 0. Okay. Two of these kets are said to be orthogonal to each other. When they are said to be orthogonal, when we know that their inner product is 0, right? So if I say that this psi is orthogonal to phi, so for example, I took the example of 1, 0. So if I just sorry, 1, 0, so this would be simply 1, and if I use another one, that is 0, 1, this will give me 0. So both of them used to forming orthonormal set of vectors. So if these are orthonormal to each other, then it would be simply 0 because phi and psi are not equal. So this would be simply 0. And what would be psi? Psi, this is the scalar product, or you can say inner product of psi with respect to itself, that it should be equal to 1. If this is the case, then we say that the kets psi and phi are orthonormal to each other. Here I would say orthogonal to each other, but if there is a normality, that is if the psi is normalized, that is if I'm trying, if I just try to find this thing and it comes out to be equal to 1, I say that my psi is normalized. So these are orthonormal to each other. Okay. So much of these things are done. Other things like Schwarzschian equality or triangles inequality, they're also important, but we'll see them quite contextually. Okay, we're going to see it when there comes a context. So all these properties are of, you can say, Hilbert spaces, and this kind of notation is called as the Dirac notation. So this is what I was teaching yesterday. So the fact of the matter is that if the fact of the matter remains that if I'm talking about quantum mechanics, the first postulate that comes out is that the state of the quantum system is described at each time by a state vector, which we represent in form of ket, and this psi t resides in the Hilbert space. And what is a Hilbert space? Hilbert space is a normed linear vector space. This is a normed linear vector space with inner product difference. Okay, so I hope this you might have got. And this particular notation in which I'm writing all these things is called as this particular thing is called as what? This particular thing is called as the Dirac notation. Okay, so this sums up a brief idea of the first postulate. I'm going to meet you in the next lecture with the second postulate. Till then, take care.